I'm Mark Renes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 2. Find the sum of all of the even-valued terms of the Fibonacci sequence up to 4 million. The Fibonacci sequence begins with two terms, 1 and 2. From there, each subsequent term is equal to the sum of the previous two. First things first, let's write a basic function to generate the Fibonacci sequence. We used Python a bit last week, so let's take a look at Ruby. Fibonacci is a function which returns an enumerator. Enumerator is a class in Ruby that lazily produces data according to an arbitrary function. The block inside our enumerator runs, and every time we pipe a value to this y argument, the enumerator provides that value back to whoever's calling for it. If you're more comfortable in Python, you can think of enumerator as being like a generator function, and y being like the yield keyword. Here, we start with a being equal to 1 and b being equal to 2. Then, at every step, we yield the value of a, the current Fibonacci value, then update the variables to add the new sum to the end. This is an infinite enumerator, so we can never completely exhaust it. In fact, Ruby has automatic big num support, so this enumerator could truly yield Fibonacci values until the operating system cuts us off from using more memory. To test it, we'll simply take the first 10. Great! We have the Fibonacci sequence. Now we just need to run some post-processing on it. Taking the sum of an infinite list sounds like a recipe for disaster. So first, we cut off our sequence when we hit 4 million. Second, eliminate any number which is not even. A few things of note for folks not familiar with Ruby. Enumerators are an example of an enumerable. Enumerable is a broader category, kind of like a Java interface, that includes anything that can be iterated over, including enumerators, arrays, hashes, which are like dictionaries, and even files if you ask nicely enough. Ruby has a big emphasis on stream-oriented capabilities. So rather than directly using a for loop to iterate over our enumerable, we generally call methods on this object, such as take while, filter, and sum in our example. Similarly, in Ruby, everything is an object. There are no primitive values like there are in Java and C++. Integers in Ruby are instances of the integer class, and one of the methods on that class is called even. The question mark is part of the method name, not a special Ruby syntax. So we run this, iterate over our enumerable, take the sum of the relevant elements, and print out the result. Everyone is happy. But again, we have 700 more challenges to complete. There's no way we want to use a wonderful, capable language like Ruby this early, and whatever language we decide to go with probably won't have nice facilities like take while and filter. So let's simplify this down as much as we can. First off, as it turns out, the Fibonacci sequence grows exponentially, which is a fancy way of saying it gets very big very fast. The first few numbers are small, 1, 2, 3, 5, 8, but believe it or not, we hit 4 million in just 33 terms. We can see this with a bit of pen and paper, or by doing some approximation techniques on the closed form of the Fibonacci sequence. So, in the spirit of keeping things simple, we really only need to take 33 terms. Now we can move our filter condition inside the function too. And all that's left is the sum. Let's take the sum and calculate it as part of the function. Now we have an ordinary function that does some math. That's a bit more palatable for some of the other languages we might consider. But there's one more thing I want to do. In Ruby, checking whether a number is even is easy. It's even a built-in function. In other languages like Python or C++, it's fairly easy too. But where we're going in a minute, it's not so easy. So if we could get rid of that complication, that would be great. Let's consider when the Fibonacci numbers are even. For our purposes, the first Fibonacci number is 1, and the second is 2. That is, we start with an odd number and an even number. If we add an odd and an even number, we get an odd number. So the third Fibonacci number has to be odd. If we add the second number, which is even, and the third number, which is odd, we get another odd number. Finally, if we add these two odd numbers together, we get an even number, and we're right back where we started, an odd and an even. The pattern repeats. No matter how far we go in the Fibonacci sequence, every third number starting with the second will be even. So rather than just checking whether a number is even or not, we can just remember where we are in the sequence. Now we have a function that, all things considered, is about as simple as it's going to get. It loops 33 times, doing some basic arithmetic and comparing some numbers for equality. Today, we'll be solving Project Euler problem number 2 in a language called, we'll call it BF. What that stands for is left to the imagination. BF is a very simple language. In fact, it only has a total of 8 commands. Left, right, increment, decrement, output, input, loop start, and loop end. That's it. All of it. But BF is Turing complete, which means, effectively, you can solve the same set of mathematical problems in BF that you could in, say, Ruby. And here we have a mathematical problem that we've just solved in Ruby. To start with, let's discuss the memory model of BF. We don't have conventional variables here. Instead, we have an infinite tape of memory. The tape is infinite in both directions and indexed by integers. Each position of the tape initially stores a 0 and can hold any integer. Yeah, as you can see, BF is a pretty vague specification. For our purposes, we'll be needing some pretty large numbers, so we'll assume we're working on a modern interpreter that doesn't have any of those restrictions. Our program has one pointer, which initially points to memory position 0. The left instruction moves the pointer 1 to the left, and the right instruction moves the pointer 1 to the right. The increment instruction changes the value we're currently pointing at by incrementing it by 1. Likewise, the decrement instruction decrements the current value we're pointing at by 1. The input instruction takes input from the user. If you're on a Linux system, this would be dev standard input. If you're running BF online, there's probably a text box for input. Regardless, the input instruction reads 1 byte from the user and stores it at the current position in the tape. We won't be using this since our program doesn't have any inputs. The output instruction takes the value of the current position and prints it out as a byte. More on that later. Finally, the two looping instructions, an open bracket and a closed bracket, must always be paired in BF. These brackets form effectively a while loop that runs as long as the value at the current position on the tape is non-zero. Specifically, when we encounter an opening bracket, if the value at the current memory position is 0, we skip the loop body and move on to the closing bracket. Conversely, when we encounter a closing bracket, if the value of the current memory position is non-zero, then we jump back to the corresponding opening bracket and run the loop again. Loops can, of course, be nested. And that's it. That's the whole language. With just those 8 instructions, we can solve any computable problem. Computable here effectively means that the problem can be solved by a computer. This includes things like addition and multiplication, and more complicated things like, say, take the derivative of this elementary function. Specifically excluded from this category are problems like the halting problem, which have a well-defined mathematical solution, but which computers can never solve. Now let's start writing some non-trivial code. This is going to get complicated, so we're going to want to break down our problem as much as possible. First, let's make a few assumptions. No part of our problem space requires negative numbers, so from here on in, we'll assume every value stored in our program is 0 or larger. Likewise, we'll only be using the right-hand side of the tape, so we'll never move the pointer further left than its starting point. Finally, just for the sake of sanity, whenever possible, we'll want every loop body to start and end at the same position on the tape. So if we move left once at the start of a loop, we should move right at the end of the loop to compensate. I'll tell you right now, that's not always possible in general, but wherever it is, we'd like to keep it simple. With that in mind, here's our very first program. Simple, right? Take a moment and see if you can figure out what this does. Pause the video if you have to. Remember, every BF program is always pointing at some position in memory. If the value we're pointing at is 0, then the opening bracket skips the program entirely, effectively doing nothing. If the value is non-zero, then we subtract 1 from it, check if it's 0 again, and repeat the loop if it isn't. Effectively, this just sets the value at the current position on the tape to 0, regardless of whatever its value started as. Now we know how to set a value to 0. Slightly more interesting, if we want the value at a position to be a specific constant number, we could just put some plus signs after that. So we could set a variable to 1, or to 2, or to 10, or to 128. Now let's do something a bit more non-trivial. This is slightly more complicated. Rather than just zeroing out a variable, we're doing some additional work every time we subtract. Let's trace it through. We start at the opening bracket. The current memory position is non-zero, so we keep going. We decrease it by 1. Then we move to the right. We add 1 to the new memory position, and then we move the pointer back to the left. Now we've hit the end of the loop. The closing bracket jumps back to the beginning of the loop if the thing we're looking at is non-zero. The thing we're looking at is 2, so we're going to jump back to the beginning of the loop. Now we do it all again. We decrement, move to the right, increment, move back to the left. After that, we've hit the end of our loop again. We need to check if the value is non-zero. It's still non-zero. Rinse and repeat. We decrement the value, move to the right, increment the value, move to the left. Now we're at the end of the loop again, but this time the value at the current memory position is 0. So we end our loop. We started with a particular number at the first memory position, and we moved it to the right one. This little program takes the value at one memory address and moves it to another. If the value to the right is non-zero, this effectively adds the value at the current position to the value on the right. We can make this a bit more elaborate if we want to do multiple additions at once. This is similar to the last one, but we add two positions on the tape at once, to the right and to the left of the starting position. This is great if we need two copies of the same data. Adding and moving are two of the most basic things we'll need to do, so we'll be writing tons of variants of this tiny little program, where the only difference is the source and target registers in a manner of speaking. Now what about if statements? We have a way to run a while loop until a value is 0, but what if we want to run a block either 0 or 1 times? Say, if the value is 0, skip the body, and if it's any other value, run the block exactly once. This is an ordinary while loop. It will run until the current memory position is 0. This is what we're going to call an if statement. You'll recognize our favorite reset to 0 program at the end. All we do is run an ordinary loop, and then, at the end, reset the value to 0 so we don't ever run again. Now this has the unfortunate side effect of destroying whatever value we had at that position, so if we still need it around, we'll need to make a copy beforehand. Fortunately, we learned how to make copies of things a few minutes ago. From these basic building blocks, we can do more complicated things. For example, let's say we want to perform a logical negation. So if the value is 0, we want to turn it into a 1, and if it's anything else at all, make it a 0. Looks complicated, right? But let's give it some better spacing. That's better. It's just a few of the programs we've already written, put together. Set our output variable to 1, then if the input value is non-zero, decrease the output value by 1. Now, let's start to build up our real solution. For this program, we'll be using registers 0 and 1 as temporary variables when we need to copy or add values. Normally, when we move values to another register in BF, the original value is lost, which is, needless to say, not how variables work in most programming languages. So when I say add x to y, what I mean is move x into our temporary register, and then move our temporary register into both x and y. That way, the original value of x is not lost. It makes the code a bit more bloated, but it becomes easier to reason about. Register 7 will be our accumulator, where we store the sum of all the Fibonacci values. Registers 10, 11, and 12 will be the current Fibonacci values. That is, these three registers will store the most recent three numbers in the Fibonacci sequence we are currently computing. Register 15 will be our global counter. It'll start at 33, and when it hits 0, that tells us to stop iterating. Register 20 will keep track of how far we are from the next even number. Register 21 will be a temporary variable used to aid us in this computation. Finally, we'll use registers 40 and beyond to print out the result. More on that later. You might be wondering why there are so many gaps in this table. At the time of writing the code, we don't always know how many registers we're going to use, so I left some padding in several places just in case. Sure, we could collapse all these down at the end, but registers are cheap, we have infinitely many of them, so I'm not losing too much sleep over it. Now, this is going to look complicated, but it's all built up from things we've already discussed so far. First, we initialize some variables. Our accumulator, in register 7, starts at 0. Our three Fibonacci values start at 0, 1, and 1, respectively. We've been starting at 1 and 2 in our previous examples, but we'll be starting at 1 and 1 here simply because it makes the loop variables line up a bit better in BF. Our counter variable, in register 15, starts at 33. Our next even variable starts at 1. Again, it started at 2 before, but we shifted our sequence back 1 to make the code a little cleaner, so it's going to start at 1 now. Just to drive the point home, this looks like a lot of gibberish, but in every case, we're moving the pointer to some desired position, using our reset to 0 program to set the variable to 0, and then adding whatever constant we want to it. So we've initialized our variables. Now we need a loop. We want to run our loop until the counter variable is 0. Fortunately, that's exactly how loops in BF work. So all we need to do is make sure the pointer is pointing to our counter in register 15 at the start and end of our loop body. Now, inside our loop, we're going to copy some variables. We want to perform the assignment A equals B. That is, we want to move the value in B at register 11 into the variable A at register 10. We're going to perform several steps to make that happen. First, we zero out register 10. Then, we zero out our temporary register. Then, we move, using a loop, the value from register 11 into registers 10 and 0. Finally, we move register 0 back to register 11. Here's how that looks in BF. Again, it looks complicated, but all of this is just building up from the programs we already discussed. As it turns out in this particular case, we don't need to move the value back into register 11, since we're about to replace it anyway. But in the spirit of treating variables consistently, it's safer to just do it all the time. Next, we do the exact same thing to copy C into B, using the temporary register again to make sure we preserve the original value. In this case, we actually do need the original value on the following line. Now, we want to add A to C. We zero out register 1, we zero out register 0, we copy A into 0 and 1 simultaneously, then we move 0 back into A. Next, we're going to move register 1 into C without zeroing out C. That way, A gets to keep its original value and we still add it to C. Let's see how that looks in the code. Next, we decrement our even counter, just as we have in previous versions of this program. Now, we want to check and see if our even counter is equal to 0. We don't have an if equal to 0 statement, but we have figured out how to do an if not equal to 0, and we know how to negate values in registers. So we're going to negate our even counter, storing the negated value in our temporary register 21, then we'll use an if statement with register 21 as the target. Inside the if statement, we know we've found an even number, so we add C, the current Fibonacci number, to our running total, using the same copy and add routine we did for C a moment ago. Then we set our even counter to 3, and set our if variable to 0 so we don't repeat this loop again. Back outside the if statement, we simply decrement our counter and move on. When the while loop sees that the counter is 0, it'll terminate. Now we have a working program. Or, at least sort of. This program will compute the correct numerical value, but we haven't printed it out yet. And as much as it would be nice if BF had a print statement, it's not so easy. The only print instruction in BF is the dot, which outputs the current tape value as a byte. And based on the problem description, our solution should be within an order of magnitude of 1,000,000. We can't print out values that large as bytes, they're not valid ASCII, and they're not even necessarily valid Unicode characters. Fortunately, this is a fairly well-studied problem, and there are standard solutions online. To avoid getting too far into the weeds, we'll simply use a standard solution from the internet that looks something like this. This code comes from EsoLang, the Esoteric Programming Languages wiki. I'll be posting a companion video where I break down this block of code, since it's fairly complex in its own right. But for now, we'll just take it as a magic black box that does what we want. And that makes a single large BF program consisting of over 1,000 characters. We can run it and get our answer, which solves Project Euler problem number 2 in BF. Tune in next week when we tackle the third problem in J, the array-based programming language.